that we're going to cover tonight. As in case you guys online didn't hear it, the material we're covering tonight will not be required for the exam. Only the sessions that we've already covered, that we've had homework assigned and exercises assigned for. I may include a problem that's based on the material from tonight, but that'll only be for if I do, it'll only be for extra credit. It won't be for basic credit. Okay, and maybe also to maybe stretch you a little bit so that like I at least give some of you guys that want to be challenged a little bit a chance to proceed a little bit ahead of us. Okay, so I'm going to close this down. And I'm going to go to our session 5. There's a Word document on there, lab exercise 615, 16. Okay, now last session, I'm about to say last week, but the summer, man, just it's like everything goes so quick here. Last session, we were discussing the idea of a normal distribution, a numeric variable that is basically, if we sample people randomly, is distributed in a certain way, certain common way, and that's a normal distribution. Most of the outcomes are somewhere near the mean, and as you get further and further away from the mean, you get fewer and fewer people that or subjects or instances where that value comes up. So for instance, I might be looking at blood pressure, right? Let's say this is blood pressure. Let's say this is diastolic is the lower number, or systolic. Yeah. Diastolic, let's say this diastolic blood pressure. And the average for American males age 35 is 80, right? So the mean of this, if I sampled it, if I took every person in the United States and measured their blood pressure, every male between 35 and 40 measured their blood pressure, this might represent the entire population. If it represents the entire population, that mean 80 would be represented by a Greek letter U, right? So that's the mean. That would indicate to me that that's the mean of the entire population, since I used the Greek letter. What else do we call that? Anybody remember? We have another name for when we have something that applies to the entire population. Call it a parameter, right? That's a parameter. Okay. So now the standard deviation would be signified by sigma. I'm going to say that the standard deviation is 10. Okay, whatever this is, milligrams of mercury per, I guess millimeters of mercury. Okay, so at any rate, the standard deviation is 10. So if this is truly a normal distribution, this distribution of blood pressures for the entire population is going to be bell-shaped. The mean is going to be in the middle. The median value, the middle person, is also going to be 80, as well as the average person, right? And it's going to be symmetrical. So if I flipped it over across the mean, it would be exactly the same shape. And I know certain rules based on the empirical rule about the distribution of the population. I may, if I didn't know what the standard deviation was, wouldn't matter. I do know, I wouldn't need this to know, even if I don't know what standard deviation is, I know that if I'm one standard deviation below the mean and one standard deviation above the mean, the number of people that are represented in that range is 68% of the population. And if I go 2 standard deviations below the mean and 2 standard deviations above the mean, 95% of the population is above or below the mean. Well, now, if knowing that, and for 3, it's 99.7. Knowing that, if I told you now that the standard deviation is equal to 5, I'll use 5 instead. Standard deviation, that's more realistic. Standard deviation is equal to 5. Well, then I would know that 68% of the population has a blood pressure between 75 and 85. One standard deviation below, one standard deviation above, and that's 68%. And 95% of the population of this population has a blood pressure between 70 and 90. Okay, and 99% of the population, 99.7 actually, 65 and 95. Right? So if this were true. Now, if the standard deviation were 7, right? what that would mean is that the distribution would look a little wider, right? And that one standard deviation to the left or the right, instead of this being 75 and 85, it would be 73 and 87, right? So the shape, the actual distribution is true for all normal distributions. The actual percentage of it from the perspective of number of standard deviations to left and right, those areas stay the same whether it looks like this or it looks like this. Difference between, matter of fact, maybe let me undo that. See if it'll let me undo it. No, not let me undo it. Okay. Okay, I'll do it. I'll do this again. Okay, worry about that. These two distributions, this one and this one, both have the same mean. Say the mean is 100. The difference between them is the standard deviation. This one, the inner one, might have a standard deviation equal to 1. The larger one, the wider one, might have a standard deviation equal to 5, let's say. Okay, the standard deviation gives us an idea of the spread. But in either case, both cases, for this skinny one here, if you're going 2 standard deviations to the left or to the right, that's 95% of population. And the bigger one, if you take its standard deviation and go 2 to the left and 2 to the right, you'll get the same area for that distribution. Okay, so that's really nice. It's an interesting tool that we can use to kind of predict something about normal distributions and so on and so forth. But we don't get to work with populations very frequently. Most of the time we're working with samples, right? So for instance, if I were to take that same population and I were to take a sample from it, right, I might find that the mean comes out to be, let's say, instead of 80, comes out to be 81. And the standard deviation, instead of being 5, comes out to be 6. Okay, and the sample size I took is equal to 25 people. Okay, well, when I take a sample from a population, right, I randomly sample 25 people from 1 million people, let's say, randomly 25 people. That sample, if I do it really, if they're all, each person is independent and I do it really randomly, the sample mean should approximate the population mean. Like, in other words, I wouldn't expect, if I took 25 people randomly and took the average of those 25 people, I wouldn't expect to get a blood pressure of 139, right? I'd expect to get a blood pressure around 80, right? Because the average, I might get some people at 75, some people at 95, so on and so forth. But on average, I would expect it to be pretty close. And in fact, intuitively, you might say to yourself, if I take a bigger sample, I think it's more likely that I would get a result for the average that's closer to what the population is. If I took a sample of 1,000, I think that's more reliable than just having a sample of, think about if I took it to the extreme. If I took a sample of 1, I might get a blood pressure of 60. I might get a blood pressure of 140. Could be anything, right? Could be anything within the whole range of blood pressures. So a small sample is less reliable at approximating the mean than a big sample is. That's intuitive. Now, we want to get beyond intuitive. We want to understand this. And we want to really be able to quantify how well we can depend, how much we can depend on the sample that we take. Because really, in 99.999% of the cases, when we're studying a population, we're never going to know the population mean. It's out of our reach because we won't have the resources to measure everybody. So if we want to know something about a population like diabetics in the United States, what's the average blood pressure of diabetics in the United States? Or what's the average blood pressure for diabetics in Manhattan, right? Or in East Harlem, for instance. We're not going to go to everybody in East Harlem. We won't have the resources to do that. However, I should hesitate a little bit. There's a study that's pretty big that the Department of Health does. It's called Community Health Survey. They don't do everybody, but they really do a pretty big sample. So anyway, so if I wanted to know what the average blood pressure is in East Harlem, I would randomly select a certain number of people. And I know that a bigger sample, more reliable, is that my result is going to be more reliable. So now it's incumbent on us to know how reliable is reliable, and how reliable do I really need it to be, right? Is it reliable enough for what I want to demonstrate? Let's say I want to prove that people in East Harlem have a higher blood pressure than people in the East Village, right? So I want to compare those two populations. I might sample a group in East Harlem. I might randomly sample people in East Harlem and compare to people randomly sampled in the East Village, and see if the average blood pressure is different for those two groups. Ideally, what I really want to know is the average population blood pressure for everybody in East Harlem different from the average for everybody in the East Village. But I don't have the resources to measure everybody. So let's see what I can do about that. Well, first of all, when I take this sample and it came out to be 81, and the standard deviation for those 25 people came out to be 6. How do I indicate what that 81 is? Is that mu? Is that the population mean? No, it's the mean of my sample, right? So what do I call it instead of mu? X bar. I'm going to use X bar to indicate what the mean is of a sample. So if you see X bar instead of mu, you know you're working with a sample. And that's not called a parameter. What do we call that now? The statistic. There you go. Exactly. Hence the name of the course. That's a statistic, right? And for 6, the standard deviation, I'm not going to use sigma. What am I going to use instead? I could use S, or I could use SD, or I could just write standard deviation, right? But I'm not going to use sigma. If you see mu or sigma, you know I'm talking about the population, not a sample. Now in this case, now you know I'm talking about a sample. And the other thing that you know about samples is that it's also important to know how big a sample it was. So if I use n, I'm talking about the sample size. Okay. So now I want to know something. I intuitively know that when I take a larger sample, I have a better chance of getting a result from the mean that's close to the real population mean. Right? But now I want to be able to quantify that a bit better. I want to know how much better a bigger sample is. I just want to depend on, I think it's a bit better. Okay, so we're going to do an exercise now. And that exercise is in this. Thanks, you guys online. I'm noticing that you're keeping up with it as well. I appreciate it. So we're gonna do an exercise. This table, there's an Excel spreadsheet, and this is the Word document for lab exercise 6. There's also an Excel spreadsheet in here as well called population of 100. This is a population of 100 people. I want to expand this a little bit so we can see a little bit better that it's alone in here. Okay, so this is 100 numbers. I put rows and columns. I put extra rows and column numbers. I probably could have stuck to the ones with Excel, but they're hard to read, so because they're small. So I put 0 to 9, 10 columns, 10 rows, right? So that means we have 100 people. Now these are measurements of some kind for people. We don't have to worry about exactly what they are. Maybe they're ages. Maybe they're not BMIs, I hope. Maybe they're, I don't know, blood sugars. Who knows what they are? It doesn't matter to us what they are. Okay, all I know is that all I know is that I took these numbers. This is this population. This is everybody in the population. That's a pretty small population, 100 people, right? But hey, listen. Sometimes populations, you can have Rhode Island has a smaller population than New York does. So its population is going to be different sizes. In this case, my population is 100 people. So if I were to take the average of all these values, that would be mu, right? Mu. Okay, what's mu equal to? Is equal to the average of all of these numbers. So my population average mu is equal to 50. That's convenient, right? Okay, I'm going to reduce this just a little bit so I can get it. So it's easy to see. Okay, mu is not. So what about my standard deviation? Sigma. Right, my standard deviation is equal to standard deviation, parentheses, and I'm going to take standard deviation of all of these numbers. And it comes out to be 9. Pretty convenient, right? Nice round numbers and stuff like that. So now I say to myself, this is my population, mu and sigma. Now let's say that this population were much bigger. So I couldn't do this. It was just too big to measure all these people and get all these numbers. So I'm forced to do a sample from this population. I am going to do a sample of size 9. Equals, okay, n is equal to size 9. And I'm going to find x bar. If I write x bar, it's just easier than putting in an x with a bar on top. And I'm going to find the standard deviation for my sample, right? The sample I'm going to take. Now, if I took a sample of size 20, it'd be better, right? 100. If I took a sample of size 25, that would be even better. I'm going to start with a sample of 9. Okay, so now I got to randomly sample 9 people from this population. There's a couple of ways I could do this. One way I could do it is I could take my finger, close my eyes, and just point at it and see which one it lands on. Is that random? Well, I'm right-handed. Chances I'm going to pick more from the right than from the left, right? So that's not exactly what you would call a random sample. So I need something that will randomly sample, truly randomly sample these. One method to do that is to use a program like Excel. Excel has a random number generator, equals RAND, parentheses, and close parentheses. It's going to generate a random number between 0 and 1. And actually, it came up 0 because I've got the cell formatted for no decimal places. Okay, now it's 2. So it really came up 0.16. If I did it again, okay, close parentheses, comes up with a number 0.4. So if I wanted to generate a random number between 1 and 10, all I would have to do is say that it's equal to this number times 10. And notice every time I hit enter, it's going to recalculate. Equals random. Equals. You already got a random number. This. Every time I touch it, it's going to recalculate. Equals the random number times 10. And that cell is rounded. So every time I hit enter, every time I do a new calculation, enter something, it's going to recalculate. So now the 2 numbers that came up with were 4 and 6. If I do it again, it might be 2 other numbers between 0 and 10, but it'll come up random. So you could do it with Excel, okay? But I know we're allergic to Excel, so I'm going to do it another way. And in fact, a lot of researchers actually prefer to do it this way. In your Session 5 folder from Blackboard, there's something called a random number table, okay? And this is from the back of one of the textbooks. Well, I'm going to go over that in one of those sessions. It gives you a description of it. It is a book published by the Rand Corporation, which using a computer program or some other technique generated a table of 1 million random numbers. It's just page after page. Imagine this, page after page of these numbers, right? All generated randomly. So now, if I want to randomly sample people that are in this population, one of the things that I could do is pick out any spot here. I'm going to start here. I'm going to start with 94. And I'm going to say 94. See that 94 there? I'm going to say that number represents row 9, column 4. So that's the person in row 9, column 4. And what is that person? Row 9, 0, 1, 2, 3, 4. It's 58. Okay, that person is 58. Okay, then I'm gonna continue across. The next one is 60. That's row 6, column 6. No, I mean row 6, column 0. Okay, which would be row 6, 0, 1, 2, 3, 4, 5, 6. Column 0 would be, or row 0 would be 58. So that number is 58 also. Coincidence. And the next one is going to be, let me go back to that. The next one is going to be 1, and I'm going to carry it across the 1, 1. Row 1, column 1. Okay, row 1, column 1 is going to be 48. Up, now I got a number that's less than 50, less than what I know the population mean to be. Okay, and I'm going to go ahead and do this 9 times. That's my random sample of 9 individuals from this population. I'm going to ask you guys to do the same thing, the guys online. Use the random number table, start wherever you want, and find 9 random numbers out of this population of 100 people. Find the average for me. Okay, so you guys do the same thing online, okay? And as you get done, I'm going to continue to do this just for my sample. As you get done, just type in or yell at me with whatever your average is. Okay, so where was I? I was over here. So my next one is row 5, column 8. Row 5. Okay, I'm going to move this out. Row 5, 0, 1, 2, 3, 4, 5, 6, 7, 8, 66. Wow, getting a lot of high numbers here. 66. Oh, okay. Oops. Oh no, what did I do here? Oh, nothing. Make that go away. Good. Next one is going to be 38. Row 3, column 8, 64. I need to organize this so I can get back and forth between these. I forgot what that was. That was 38, I think. Yeah, 38. 3, 8, 60. Did I already put the 64 in? No, I didn't. I'm going to double up here, put it up there. 64. Next one's going to be 16. And I'm not going to be concerned with the fact that it looks like it's coming off a little weird because I really want it to be random. 16 is the next one. 1, 6. 1 and 6 will be 48. A lot of you are going to get numbers that are higher than averages, higher than 50. Some of you are going to get lower. 80, 54. Okay. 5, 6, I think is the next one. 5, 6, and 1, 0. 5, 6, 46, and 1, 0 is 65. 46 and what was that? 65. And the last one is 04, 04. So row 0, column 4, which is 58. Boy, I pretty consistently found them above the average, but that's okay. Nice. What was that again? 4? Did I say 54? Okay. Oh, actually, I can eliminate that one. I didn't need that one. I only need 9. I only need 9 people. So I'm going to take the average. Equals the average of all these numbers. And it comes out to be an average of 56. So our first sample is 56. Okay, let's see what everybody got online here. Okay, I got a 50. I got a 50.67. I'm going to call that a 51 just to keep things a little simple. 55. Okay, how about you guys here? Is that another 50 back there? 50? 47? Anybody else? You guys have an idea what I'm doing here? Oh, well, you're looking at that and like I'm moving it around, so I'm making you crazy, right? Is that what's going on? You can download it to your computers from Blackboard. Okay. Okay, got another. Is that a new 50 that I got there? No, I don't think so. I think it's the same people. Okay. Good. Anybody else? Another volunteer? Hi, how you doing? What I'm doing is I'm using the random number table. See, like in other words, this is a population of 100 people and the values that I got for that this is the values for 100 people, whatever measurement it happens to be, blood pressure, blood sugar, whatever. Okay, so I want to randomly sample people from this population. I want a sample size of 9. So I could just go in here and say, oh, this person, this person, this person, this person, just randomly point at them. But that's not really random. I have some bias. I may point to the left more often than the right. I may inadvertently point to higher numbers or lower numbers. So I want you guys to sample 9 people there randomly. So the way to do that is you take a random number table. This table, oh, I see that one. Okay. This table is derived from a listing of numbers that was generated randomly. So you could start anywhere here. Like I'm going to start this time at 41. And you could say, well, I'm going to take the person that's in column 4, row 1. I'm going to take the next person. I'm going to pick the person that's in row 1, column 9, right? So it's kind of like taking your finger and making a random pattern. But in this case, somebody that really has created a random pattern is telling you which people to take. Okay? So anybody else online feel adventurous there? Okay, I need 1 or 2 more numbers. Would help. Okay, anybody else want to hazard a guess? 49, okay, good. Okay, how about 1 more? You know, you could actually do this with your finger and do them randomly. I'm not looking over your shoulders. I wouldn't know. 50? 50 was it? 58? Okay, good. Okay, how about 1 more? Make it an even 8. Anybody else? Oh, and no, you don't want to skip it. In real life, a person online asks, what if the random table gives you the same person twice? Like if it says 45, 45. Well, that's it's a random table, right? So the idea is that most populations are so large that, like for instance, if I had a drawer with 3 socks in it, right? 2 black ones and 1 red one. If I pulled a sock out and didn't put it back, now all of a sudden it changes the odds of me picking out a red or a black sock, right? Because I didn't put it back. And now, instead of 2 to 1, now there's an even number of different colors. With a big population, you don't have to worry about that. If you pull this person out and he turns out to be, his number comes out to be 60, you don't have to worry about the fact that, now it's missing a 60, so you won't be able to pick a 60. You don't have to replace them. So assume for our purposes, you could pick the same person out more than once. Kind of like he's replacing 56. Okay, let's stop. Okay, so now I am going to take the average of these averages. Notice what I'm doing now. I'm not taking the average of anybody from the population. I'm taking the average of the averages, right? These are all averages people calculated. Okay, whoops. Average of these numbers. And the average comes out to be 53. Okay, so now we missed it a little bit, right? Okay, so now I'm going to take the standard deviation of these numbers. Now, this is not the standard deviation of the population. It's the standard deviation of the means of sample size 9, right? Repeated samples of sample size 9. Oops, I didn't parenthesize it. Parentheses. Okay, and the standard deviation comes out to be 4. Okay, so the mean approximates the population mean, right? If you looked at this, there's people in here 69, 40, 30 something. They're all, they're really pretty much all over the place, right? So 53 is not that bad an approximation. It's certainly better than if I had just picked out someone randomly and I could have picked 61 or 38 or something like that. It's not really that bad of an approximation. However, so it's the mean when I take repeated samples and then find the sample mean of the repeated samples, right? I approximate the population mean. If you think about it, it kind of makes sense because usually what will happen is half the time you'll be below the population mean, half the time you'll be above the population mean when you take samples from the population. So, so they'll basically even out. But what happened to the standard deviations? The standard deviation is less than half of what it was for the population. The standard deviation, the mean of repeated samples of the mean from the population of the same size, the means tend to be the same as the population mean, right? But the spread tends to be less. The standard deviation is less. Think about that. Why is that occurring? Because if I look at the original numbers, they go from 38 to 69, right? Big spread, right? But now I'll never get a sample with 9 people in it that are 69. So I'll never get a sample mean of size 9, a sample of size 9 that has a mean of 69 because only one person had 69. It's always going to be closer to the mean. So when you take repeated samples, they're always going to be closer to the mean than the range of the actual population. So what does that mean? That means that, and I'm going to show you a relationship now. Okay, we kind of did that. Where did my notepad go? Okay, there it is. I'm going to get a new page. That means, for instance, that if I started with a population where the mean, this is a population now, the mean is 100, right? Population mean is equal to 100. The standard deviation, sigma, for the population, let's say is 12. Okay, so now if I were to take samples from this population, I take samples of size 9 from this population, and I repeated that over and over and over and over again, many, many, many times. If I took those sample averages, not the original population, but the average from all those repeated samples of size 9 like we just did, then what's going to happen is if I make a new distribution from all those sample means, half of them are going to be below 100, half of them are going to be above 100. So the mean for all of those is going to be 100 also, roughly 100 also. Not exactly, but roughly 100 also. But the main difference is that they're not going to be spread out as much. The standard deviation is going to be smaller than the population standard deviation because the nature of taking those samples makes them numbers that are closer together, right? I'm going to teach you a trick over here. The standard deviation is dependent on the sample size. Sample size is 9. The standard deviation is equal to the standard deviation of the population divided by the square root of the sample size. Okay, so I only did it for from a standard deviation of 9 what was it before? I think standard deviation was 9 for that population. When I took sample sizes of size 9, and I took the standard deviation of the 8 values that we have, it turned out to be 4. Theoretically, it should have been 9 divided by the square root of the sample size 9, 9 divided by 3, which would be a standard. We were pretty close, right? So that's the nature of sampling. Now, what about, so this is going to be, the standard deviation, if it's sample size 9, is going to be equal to 12 divided by the square root of the sample size. Sample size was 9, 3. So the standard deviation of these repeated samples of size 9 is going to be 4. Well, how about if I take a sample size of 16? Right? Well, now the standard deviation is going to be equal to standard deviation of the square root of n, which is now square root of 16, which is 4. That's going to be equal to 3. Right? Well, how about if I take a sample size if I keep increasing the sample size, what happens is as you increase the sample size, your distribution gets narrower and narrower. So basically, what we've just demonstrated is that by increasing the sample size, we can quantify how much narrower, how much closer to the mean each one of the values is likely to be for the sample means that we're taking. And we can use this as a tool now. So I'm going to go over here, and we're going to work out a couple of problems that are going to take advantage of this. Okay, so let's take a look at this. Well, first of all, number one, this first problem is just a reprise of what we did before. So I'll just do it verbally. If the total cholesterol values for a certain population in an approximately normally distributed population is 200, and the standard deviation of 20, find the probability that an individual picked at random from this population, sample size 1, right, individual, is between 80 and 220. Well, we know that's one standard deviation above and below, so it's 68%. Between 160 and 240, we know that's 2 below, 2 above. That's going to be 95% is the probability. Greater than 225, we'd have to do the z-score and figure out what area is below it, and then subtract it from 1, so on and so forth. Well, now let's take a look at this. Now, I am going to take a look at the property of samples. We take a sample of size 25 from that same population, right? So if I take a sample of size 25 and the standard deviation of the population is 20, what's the standard deviation for all of the samples of that size that I might take? Well, the sample size is 25. So the standard deviation for repeated samples of size 25 is going to be 20 sigma divided by the square root of the sample size, 25, which is 5. So 20 over 5, right, is going to be 4. So our new standard deviation for the samples is going to be 4. Now I'm going to throw a little nomenclature out here. Let me get a fresh sheet here. So our new distribution, which is samples, sample means, we expect it to have the same mean as the population, which is 200, right? But now we expect our standard deviation for all the sample means to, instead of being 20, to be 20 over the square root of the sample size, which is equal to 20 over 5, which is equal to 4. We expect it to have a standard deviation of 4. We're going to, now we can use that now to say, well, gee, how, if I were to take a sample from this population, what's the problem? If I took a sample of size, standard deviation is before, if I took a sample of size 20, of size, n is equal to 25, what's the probability that I would get a result between 180 and 220 for my sample mean? Well, my sample mean, remember now, is distributed differently than my population mean. So my sample standard deviation is going to be equal to 4. So 180 now is not one standard deviation below the mean I would expect. It's now 5 standard deviations below. So really 180 would be way down here and 220 be way up here. So what percentage, what range of values would I expect to be one standard deviation below and one standard deviation above for our sample means? Well, I would expect it only be 4 below, or 196, to 204. I would expect 68% of our sample means, if we did it over and over again, to be between 196 and 204. Now, if I took a sample size of 100, right? Now, my new standard deviation for all the sample means of size 100 my standard deviation is going to be equal to 20 divided by the square root of 100, which is 10. That's going to be equal to 2. So now I would expect 95% of my sample means of size 100 to be between two standard deviations between 196 and 204. Now 95% of them between those two, and 68% between 198 and 202. Right? So see how the nature of taking a large sample affects what the distribution is for those samples. So the mean stays the same of this new kind of distribution, but it gets narrower. Well, this is really interesting now because it's going to help us as we move forward to quantify how well we can trust the result of a sample. And we're about to see that in a second. Okay, let's see. Let's go back to this chart table. Okay, sample size. What's the probability that a sample of that mean is larger than 204? Okay, well, didn't we just do that? Probability that it's larger than 204. Well, 204 is one standard deviation. This was 32%. This is 68%. This is 16%. So the chances that it would be larger than 204 is 16%. Okay, just like we did before, except that we're using this standard deviation for the means, not the standard deviation for the population, but standard deviation for the means. Okay, you want to know something? It's very confusing, right? Yeah. This idea, standard deviation for the population results themselves versus the standard deviations for all the samples that I would take repeatedly of the same size, the results of all those averages. Why don't we give that standard deviation for the means of a certain size, why don't we give it a new name? Instead of calling it the standard deviation, we're going to give it a new name, and we're going to call it the standard error. Okay? That's the name that we're going to assign to this. So now on, when I say the standard error, you know I'm talking about the distribution of means of a certain means from samples of a certain size. Okay, repeatedly sampling a population with that size sample. Okay, if I talk about standard deviation, I'm probably talking about either an individual sample or I'm talking about the population. Okay, so standard error is in order to know the standard error, we have to know the standard deviation of the population, and we need to know the sample size. Okay, and it gives us an idea that if I were repeatedly to go in and randomly sample a population, what the range of values I would get for those means when I calculated it from that sample. Okay, so let's apply this a little bit more. Except now we know it's called the standard error. Okay, and this is going to kind of become a little bit clearer now why this is so valuable to us in pretty short order. Okay, so what's the probability that the mean of the sample is between 192 and 204? Well, 192 is two standard deviations below the mean, these sample means, and 204 is one standard deviation above the mean. So you know that we would, using the empirical formula, we would do this whole deal with, okay, this is what was this? This was 200. So 204, remember the standard error, because we're still working with this sample size of 25. That's 204, that's one standard deviation above, and 192 is two standard deviations below, minus z-score minus 2. So we know that this is 50% and this is 32%, right? Half of the 16. So this is 32 and 50 is 82%, right? From there down, right? But we know that this area here, two standard deviations, well, that represents 95%. How much is left in the tail? If that's 95%, it's between here and here. 2.5%, right? Exactly, right? On the top end, too, it would be symmetrical, 2.5%, right? So how much is this area in between these two? Well, it's equal to the 82% minus the 2.5% that's below the 192. So the percentage of results sample means that we would get between 192 and 204 would be, that would come up 79.5% of the time, right? 82 minus 2.5. Okay, and we could go on and do this over and over and over again. You can practice this with some of the other other elements here. Okay, and we can move on. I want to move on to something that a way that we're going to actually wind up applying this. High efficiency dishwashers. Because we're interested. The reason, good question. The reason why I'm gonna, let me do this again a little bit more clearly. Okay, so we're interested to know what percentage of the time we would get a mean for our sample of size 25, right? What percentage of the time our standard error, right? Our standard error is equal to 4. We figured that out. How do we find that? Sigma over the square root of 25. Sigma was 20, right? So that's 4, right? Standard error is 4. So that's our this is our distribution of mean averages to means for that sample size. So we're asked, what's the probability of getting a result between 192 and 204? Right? So we want to know what this area is in here. Right? Right? So what I did was I said, okay, if I start from the 204 and go left, that's 82% of the possible outcomes. So that includes this. So in order to find what's between here and here, I have to subtract this. So this I know because this is 2 standard deviations this way. If I had 2 standard deviations this way, that's 95%. So only 5% left. So since it's symmetrical, half of that 5% has to be there and the other half over here. So I need to cut off that 2.5% to know how much, what percentage of the area of this distribution is between those. No, you're still not comfortable with that?
Because the first one's 68, meaning 34, plus there will be 2. 34.
Oh, did I say 30? What's that?
So that's 34, 34, and 14. So that makes 82. Without, you don't have to minus that.
I'm sorry, let me start again. Yeah, you're right. I said 32. This is actually 34, right?
34,
Okay, 34
and
minus.
standard
Oh, no, no.
14.
This is 2 standard deviations below,
Yes,
not
that
1.
means it's 34 and 14. The first standard is 34, 34. The second standard has 13.1. So 14.
No, no, no. Back up. Wait, stop for a second. 2 standard deviations apart is 95%, right?
Yes.
Yeah, but it's only 1 on the one side and 2 on the other.
Right.
Right.
That's why on this end here, right? In other words, we need to know what is this area
Would it
here?
be 68, the 2 middle one plus the 13?
Yeah. So the 14, so it's 82.
Where are you getting the 13? I'm not sure where the 13 is coming
68
from.
are the 2 middle ones?
Is 13.1 or 14, whatever you want to call it. You know, like, because it's, so it's 34, 34, 14.
Wait.
14,
Let me wait for a second.
First you get the 68.
Here's the mean, right? So if I go over here to 192 minus 2 standard deviations, what's this area in here?
That's 34 for 14, it's 48.
47 and a half. Okay, 47 and a half. Okay, and what's the area over here?
34.
34, and if I add them together?
81 point something, so that means 82.
Right. Now watch how I'm doing it. I'm saying that this is one standard deviation to the left of the mean, and this is 2 standard to the right of the mean, and 2 standard deviations to the left. So this from here down is equal to 34 plus 50, the entire thing. So that's 84%.
Minus 2 something.
Minus the 2.5. So we're getting the same. We're doing the same thing.
Yes, but you messed up over
there. Yeah, because I put 30. I put 32.
Yeah.
I put that because I put 32 instead of right. Okay. Yep. So we are doing the same thing. You've heard the expression that there's many ways to skin a cat, right? So this is one of many ways to skin a cat. So at any rate, So, okay, you guys online got that too, right? So you see what we're doing here. We're working now with sample means, repeated sample means, because we want to understand what's the impact of taking a sample size 25, a sample size, uh, 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 yeah, sample size 100, sample size 1,000, and so on. Okay, so now I'm gonna create a new example on the fly, and I'm gonna say to myself, okay, so now I go and I sample a population. Okay, and I'm going to take a sample size of 25, right? And I find that my mean from that sample is equal to 100, right? And I know somebody tells me, a little birdie tells me, the standard deviation for this population happens to be 10. Okay, somebody's got to tell me that, right? For the moment, generally we never know what the population standard deviation, but just for now, we're going to assume that we know it. Standard deviation is equal to 10. Okay, so now if I were to, the mean is equal to 100. So I don't know what's mu. I don't know what mu is. I have no chance to know. I may never know what mu is. All I know is what my sample mean is, right? So now I know that I got a sample size, I got a sample mean of 100. And I know that if I, for the moment, say that's my population mean, just for the moment, I say that's my population mean, kind of look at it that way. And I say to myself, well, I know that that may not necessarily be my actual population mean, right? So let me think about this. Let's say I put this in the middle of all of my different mean outcomes for size 25, right? So if I look at my standard error and I say to myself, well, what if I look at this not as just a mean of 100, but let's say that I'm going to assume that I'm perfectly happy being 95% certain most of the time. I use statistics. If I were a physicist and I dropped a ball, I would know that that ball goes when it goes 3 feet exactly what the velocity is all the time. It's physics. It's a different kind of science. It's a physical science. We know exactly what's going to happen. With statistics, we're dealing with situations where probability is being involved. One time I might take a sample and get 100. Another time, same size sample, I may get 98. Another time I might get 97. Right? So we're dealing with certain levels of uncertainty or probability. So I'm going to say to myself, I'm happy being right 95% of the time and being wrong less than 5% of the time. Right? I'm satisfied with that level of certainty. Well, now, if my mean is 100, right? If my real mean is 100, right? And I took a sample of size 25, right? What would be the range of 95% of the outcomes for that population if I took sample means of that size 25? Well, 95% of the time, they would be 2 standard errors below or 2 standard errors above my sample means from that population. And what would that be? That would be equal to 100 plus or minus, right? 2 standard deviations, 2 times the standard deviation. Plus or minus 2 times. Actually, in this case, we're talking about sample means, so 2 standard errors. So if I knew the population mean was 100, I could add or subtract 2 times 2 standard errors. Okay, in our case, what's the standard error for a sample size of 25? If the standard deviation is 10, it's equal to, over the square root, it's equal to 2. Standard error is equal to 2. So, in a sense, I could say that I would expect 95% of my samples to come up 100 minus 2 times 2 is 4, and 100 plus 4, between 96 and 104. Well, we don't really know what the population mean is, right? We just assumed it to be 100. If I take a sample and it comes out to be 99, right? I can take advantage of this. And I can say to myself, my sample mean came out to be 99, right? Now, I know the standard deviation and I know the sample size I took. How about if I say I'm going to start with that 99 and then I'm going to add and subtract 2 standard errors from that to account for the level of uncertainty that I have given the variability of the original population. Okay, so what would that be? That would be 99 plus or minus 4, right? So what I'm saying is, even though my mean came out to be 99, I'm 95% certain the real population mean is likely to be between 95 and 103, right? I'm 95% sure. How far apart, how much would I have to add and subtract to be 99% sure? Right, 99.7% sure. Exactly 3 stands. So you get the idea here, right? So now I'm satisfied with 95. We have a name for that. Anybody want to guess what the name for that is? You've seen it on every abstract you've ever read. We took a population of 100 children from this that were living in certain kind of housing, and their blood lead levels was 13 plus or minus 2.3. What was that called? What's that called? It's called an interval, above and below the mean that they found. Right? What kind of interval? Confidence interval. Does it say? Does it say? Oh, somebody put that up there. Excellent, excellent. That's what happened. All these geniuses are online, and I don't pay attention to them. Okay, it's confidence interval. What kind of confidence interval is this one? What's our level of certainty? 95%. It's a 95% confidence interval. Now, let's say that I wanted to be 99% confident that when I gave you a range, the true population mean would be within that range. Is my 99% confidence interval going to be wider or narrower than my 95%? Wider. Why is it going to be wider? It's going to be wider because we want a greater certainty that we capture the real mean. So if I'm satisfied with a 90% confidence interval, my confidence interval is going to be narrower. And what's going to determine the width is going to be the standard error and the number and the z-score that we use. I'm going to tell you a dirty little secret now. When you calculate the 95% confidence interval, do you see most people? Are we going to use 2? Is it really 2? 2 is from the empirical formula. It's an estimate. You guys happen to remember what was 2.5% when we looked it up on the z table? 2.5% to the left and 2.5%. What z-score you needed to have 2.5% as a cutoff? Remember the number? 1.96. If I bring up the z table and I look up for the area that gives me 2.5% to the left and 2.5% to the right, the tails, so I get everything else is 95% is in between, it's going to actually be 1.96. Let's check, see if I'm telling you the truth. Okay. I usually won't lie to you, but occasionally, if I'm pressed for time, I might. Let's see. Z table. I hope not anyway. Okay, let's say it's 1.96, 1.90, 1, 2, 3, 4, 5. There you go. Bingo. Exactly. 0.250. Okay, and on the other end, 1.96, 0.9750. Right? So that's what we really. So if I want a 90% confidence interval, what number would I use instead of 1.96 times the standard error? If I wanted a 90% confidence interval, I would use. Let's look for. So it would be, for instance, we 5% on one end, 5% on the other. So we want to find 5%. What represents what z-score represents an area of 5% of the outcomes? It's going to be about there. 1.64, right, would be what we would use to multiply the standard error for a 90% confidence. How about 99% confidence interval? That would be 0.5% below on the bottom, 0.5% on the top. So 0.005, 0.005. That looks like it would be about. This looks like about the closest here. 2.58. Right. So we would use those numbers as multipliers, and that's why the confidence interval, even though the standard error is the same, the confidence interval is wide. It has to be wider if you want a higher level of confidence. Okay, confidence intervals. Now, this is really the first statistics that you looked at that you can go to studies and actually see them quote this. So, for instance, they might compare 2 groups. Now, a real professional statistician will cringe a little when I say this. Intuitively, it makes sense. There's reasons why you don't necessarily use this way. You don't have to worry about it at this stage. But think about this. If I told you that children that live in housing projects in New York City have an average blood lead level of 7.3, right? Plus or minus 7 point, with an average of 7.3, with a 95% confidence interval of 6 to 8, let's say 7, a 95% confidence interval of 6 to 8, right? And children that live in private housing in New York City have an average blood lead level of 7.5 with a confidence interval from 7 to 9. So, I'm sorry, 7.5 from 7 to 8. So we have 6 to 7, 7 to 8. Oh, I messed it up. Hang on a second. I'm going to have to write it down for this to make sense. Actually, I'm going to draw a number line, make it even more intuitive. Okay, so here's children. Children in housing projects have an average blood lead level of 7 with a confidence interval of 5 to 9. That's our confidence interval, is 5, 9. Okay, so the average for the sample that we took was 7. Okay, now I take children that live in private housing in New York City, and they have an average of 8. Does it look like children in private housing have a higher blood lead level than children in the housing projects? Based on that, you're nodding your head. I got an 8. The other one I got 7 as an average. Wouldn't that suggest to you it's higher? Oh, wait a second. What's the level of uncertainty? What's our confidence interval? What's the real population? I mean, not just my sample. Well, now I might say, well, it might be, maybe it's not all that wide. Maybe this goes from 7, the confidence interval goes from 7 to 9, right? Well, look, there's overlap between these two, right? The true population mean for these children is anywhere from 7 to 9 with 95% certainty. For these, it's anywhere from 5 to 9. So even though the average for these guys was higher than the average for these guys, I can't really say with 95% certainty that they're really different. What would I like to see? I would like to see 7 with a confidence interval of, say, 6 to 8, and this other group, level of 9 with a confidence interval, say 10, with a confidence interval of 9 to 11. So what's happening there? That means we're 95% certain the population mean is between 9 and 11 for this group, and the population mean is between 8 and 6 for this group. They don't overlap. So I'm 95% certain that they're different. Right? Somewhere there's a statistician spinning in his grave somewhere because they don't like using confidence intervals this way. There's reasons. There's other kinds of tests that we're going to use later on that are more appropriate than comparing the spread of than comparing whether confidence intervals overlap. There's going to be, for instance, for this, there's something called a t-test, which is a better way to do this. But this actually, for our purposes, for right now, this is pretty close to what we would get for a result for that t-test.